Let's solve question 3 from worksheet 0411, also known as worksheet number 13. So initially at time 0, switch 1 is open as drawn, but switch S2 is closed. What is the current through R2? And I'm going to label it this way. I'll call this I2. And then I'm going to call this I1. So if the switch S1 is open, then I2 equals I1. And the loop rule would just say the battery EMF minus I1 R1 minus I2 R2 equals 0, going clockwise out of the plus terminal of the battery around this loop back to the minus terminal of the battery. Since I2 equals I1, that gives us that those currents are the battery EMF divided by R1 plus R2, which is 1 amp, or 1.00 amp to 3 significant figures. So that current flows to the right through R1 and then down through R2. Now, after the switches have been in this very same configuration for a long time, what is the charge Q on the capacitor, no matter what was happening at time 0 on the capacitor? Well, you know, this is after a very long time, you see this capacitor can discharge through this resistor network. So we're going to have Q equals 0 after the switches have been in this configuration for a long time. Usually we tell you exactly what's happening at time 0, but I thought in this case, here, let's just leave the switch closed, and then it doesn't matter what Q was at time 0, you know that after a long time, Q will be 0. Now, we're going to open switch 2, and we're going to reset the clock and close switch 1. So now we know Q equaled 0 before we reset the clock. We opened switch 2, we closed switch 1 at time 0, and then an instant after we closed switch 1, what is the charge in the capacitor? It still equals 0. What's the current I1 through R1? What's the current I2 through R2? And then also, what's the current I3 through R3? And let's figure out, okay, I indicated my directions. If they come out positive, they're going to be the directions I drew them. So we know that I1 equals I2 plus I3. And we could write the loop rule. The loop rule says the battery EMF minus I1 R1 minus I2 R2 equals 0. And we know the battery EMF minus I1 R1 minus I3 R3 minus Q over C. And so here's my convention. This is plus Q on the top plate minus Q on the bottom plate. That lets me write Q over C this way. But actually, at this point, that doesn't matter because we still have Q equals 0. So actually, what you can notice here, which is the same thing you would notice by doing the loop rule up this and down this. So if you did the loop rule just for this little loop, because Q over C equals 0, we know that I2 R2 is the same as I3 R3. In other words, resistors R2 and R3 are in parallel because Q over C is 0 here. So that's kind of a shortcut we can take. We then know I1 equals the battery EMF divided by R1 plus the parallel combination of R2 and R3. You could get all of that to fall out of the math, but I think you can see it from the fact that R2 and R3 are basically in parallel because when there's no charge in this capacitor, that capacitor looks like a wire. So then it's really as if the capacitor were just replaced by a wire and you have R2 and R3 are in parallel there. Remember that switch S2 is open. So then if you just want to figure out the current through R1, well, you say, well, I go up through the battery, I go to the right through R1, and then I go down through this parallel combination of R2 and R3. Then this is 3 volts, R1 is 1 ohm, and then 2 ohms parallel 1 ohm is 2/3 of an ohm. So this is 3 volts divided by 5/3 of an ohm. That is 9/5 of an amp, or 1.8 amps, or 1.80 amps to 3 sig figs. Then, to get I2, we could just use this equation, and we say the battery EMF minus I1 R1 minus I2 R2 equals 0. Well, that's just copying that. So then we have I2 is the battery EMF minus I1 R1 divided by R2. So this is 3 volts minus 1.8 volts divided by 2 ohms. That's 1.2 volts divided by 2 ohms. That's 0.6 amps, or 0.600 amps to 3 sig figs. So, and again, remember Q equals 0 at this point. So I3 is the battery EMF minus I1 R1 over R3. That's the same numerator. That's 1.2 volts divided by 1 ohm is 1.2 amps. And then as a check, these two paths are in parallel. This resistance is half of this resistance, so the current here should be twice this, and then they should add up to this. So this current should be 2/3 of this, and this current should be 1/3 of this. So I2 should be 1/3 of I1. 1/3 of I1 is 0.6 amps, and 2/3 of I1 should be here, and that's 1.2 amps. So that makes sense. After a long time, so a long time after we closed S1, what are all of these currents? So if we say t goes to infinity, then we know that q goes to some asymptotic value. So that means dq dt, which is the same as I3, must be 0. That's convenient because now I2 equals I1. Then I think we're back to this situation we had before we closed switch S1. We have the battery EMF minus I1 R1 minus I2 R2 equals 0, but these currents are the same. So we have I2 equals I1 is the battery EMF divided by R1 plus R2. That is just 1 amp, which is an answer we got earlier before we closed this switch. So I3 is 0, I2 and I1 are both 1.00 amp. And then what's the charge on the capacitor? We can use this equation without anything crossed out. That says the battery EMF minus I1 R1 minus I3 R3 minus Q over C equals 0. Now actually the term we cross out is I3 R3 because we know the capacitor charge is constant, so I3 is 0. So this gives us that the charge on the capacitor must be the battery EMF minus I1 R1, which is the same thing actually as I1 R2 times the capacitance. So that would be the same thing as saying this is I2 R2C, by the way. Maybe this version of it is easier. I2 is 1 amp. 1 amp times 2 ohms is 2 volts. So this is 2 volts times 1 microfarad equals 2 microcoulombs. 2.00 microcoulombs to 3 significant figures. Now I tell you that at t is 1 time constant after the switch was closed, which is 5, turns out the time constant is 5/3 of a microsecond, 1.667 microseconds. Then this charge is 1 minus e to the minus t over tau. So that's 1 minus e to the minus 1. 1 minus e to the minus 1 is like 63%, it's 0.6321, times this 2 microcoulomb value, so that's 1.2642 microcoulombs. So I don't tell you exactly why the time constant has this value. I think that's a little beyond the scope of this course, but it turns out the RC time constant doesn't care what this voltage is. So you could make this voltage equal 0. Making this voltage equal 0 is the same thing as replacing it with a wire. Also, for the same configuration of resistors and capacitors, the RC time constant shouldn't care whether you're charging or discharging. So let's replace this battery with a wire, and let's pretend that initially there's some charge in this capacitor and we got a discharge. The time constant for discharging, if it's the same network, should be the same as the time constant for charging. So you can see that this capacitor would discharge through R3 in series with R1 and R2, which are in parallel. So you see it's R3 plus the parallel combination of R1 and R2. So that's 1 plus 2/3. 1 plus 2/3 is 5/3. 5/3 of an ohm times 1 microfarad is 5/3 of a microsecond. I think that's too tricky. Anyway, that's FYI if you want to know where that came from. So given that this is a time constant and 1 time constant later, then we have this charge on the capacitor. We never gave you a problem that made you do this before, so I thought this would be interesting. So now I want us to use the loop rule. Like usually when we use the loop rule, either we say, oh, this current is 0, or this charge is 0. But this is neither of those cases. So it's a little more tedious use of the loop rule. So we'll do this loop. This says the battery EMF minus I1 R1 minus I2 R2 equals 0. That's fine. Let's do this loop. This loop is going to give us an equation relating I2 and I3, and that's going to be convenient because then we can eliminate one of them. So let's actually do this loop. And we could do this loop, that would be fine. And then if we did that, we could subtract those two equations and we get the equation I'm going to write down here. Let's just directly write down the equation by going up through R2 and then down through R3, back down through the capacitor. So we start here. We go up through this resistor. So this is plus I2 R2. And now down through R3. That's minus I3 R3, and then minus Q over C, and we know Q over C equals 0. This lets us eliminate I3 and solve for I2. So let's solve this for I3. So we get I3 R3 equals I2 R2 minus Q over C. And then let's divide by R3. That gives us I3 equals R2 over R3 is 2. So this is 2I2. Q over C is 1.2642 volts because C is 1 microfarad. So Q over R3C, R3 is 1 ohm. So this is 1.2642 amps is Q over R3C. Now we use I1 equals I2 plus I3, and we plug that in here, and we get 3 volts minus I2 plus I3. This is I2 plus I3 times R1. I2 plus I3. So this is I2 plus I3. 2I2 minus 1.2642 amps. And then times R1, which is 1 ohm. And then minus I2 R2. So this is I2 times 2 ohms equals 0. So the only unknown here is I2, which we can solve for. Okay, so if you divide every term here by 1 ohm, divide out to 1 ohm, then you get this line. Everything's in amps here on this line, and then you can combine and you get I2 is 4.2642 amps divided by 5, which is 0.8528 amps. Then you get I3 is 2I2 minus 1.2642 amps, and that works out to be 0.441 amps. That's a big mess. And then I1 equals I2 plus I3, and that works out to be 1.29 amps. That's a huge mess. We would never make you do that on an exam, but what the heck. The algebra is pretty dull, but the interesting thing is that you see you can actually write down the loop rule when this Q over C term is non-zero and this current is also non-zero. That's the only reason I wanted you to do that. Otherwise, this algebra, I'm sorry, it's kind of annoying. Okay, now we're basically going to forget this part and go back to this state where we had 2 microcoulombs on the capacitor after a very long time. And it's after this point where we have 2 microcoulombs on the capacitor, we're going to reset the clock again. And now we're going to open this switch, close this switch, we're going to let the capacitor drain up through R3 and down through the parallel combination of R4 and R5. So after a long time with S1 closed and S2 open, we found that the charge on the capacitor was 2 microcoulombs with plus Q on this top plate, minus Q on the bottom plate. Now we open S1, we reset the clock, we close S2. Now immediately after, so at T equals 0 plus, we have Q equals 2 microcoulombs, so 2.00 microcoulombs. It's plus on the top plate, minus on the bottom plate. Now I3 is up. So the direction of I3 changed, this current through R3. And we could use the loop rule here. So we can say Q over C. We're looping this way, clockwise. The loop goes the same way as I3. So minus I3 R3. Oh, now we know that I3 equals I4 plus I5. You see, here is I5 and here's I4. They're both downward. We can replace R4 and R5 for this loop with an equivalent resistance. This is going to make our life a lot easier. So here's I3, which is I4 plus R5. And this is the equivalent parallel resistance of R4 and R5. So I'm going to call that R4 in parallel with R5. That equals 0. So we went around this loop. And one little cheat is that we replaced R4 and R5 with their parallel combination. And 6 parallel 3 is 2, it turns out, so 2 ohms. R4 parallel R5 is 1 over 6 ohms plus 1 over 3 ohms, reciprocal of all that. That's going to turn out to be 2 ohms. You can also say 6 times 3 is 18, divided by 6 plus 3 is 9. 18 over 9 is 2. Or I think I told you once before, 6 parallel 6 is 3. Like if you have 2 of the same thing in parallel, it's just half. So 6 parallel 6 is 3. So this 3 is actually like 6 parallel 6. So this is like 6 parallel 6 parallel 6. That's like 6 divided by 3 is 2. No matter how you slice it, this is 2 ohms, these two things in parallel. This C is 1 microfarad, so Q over C is 1 volt. So this is 1 volt minus I3 times 1 ohm minus I3 times 2 ohms equals 0. Would have been better to delay putting in numbers one more little step. So I3 actually is Q over C divided by R3 plus the parallel combination of R4 and R5. That is 2 volts divided by 1 ohm plus 2 ohms. So that's 2 volts divided by 3 ohms. That's 2/3 of an amp, okay, or 0.667 amps. That's up. I4 down is going to turn out to be 1/3 of I3 because you know that I4 and I5 add up. I4 and I5 add up to I3, and you know that I4 must be 1/2 of I5. So this is actually, it's like a 2-to-1 ratio, and they add up to I3. So I4 down is actually 1/3 of I3. So that would be 2/9 of an amp, which is 0.222 amps. And I5 down is 2/3 of I3, which would be 4/9 of an amp, which is 0.4444 amps. Another way to do that is you can say Q over C minus I3 R3 minus I4 R4 equals 0. If you wanted to do that just to get I4, that would get you I4 equals, Q over C was 2 volts, and then I3 was 2/3 of an amp, times R3 is 1 ohm. That would be 2/3 of a volt. And then we could divide by R4, which is 6 ohms. The next part of the question says, what happens at t goes to infinity? So a very long time after we close this switch, well, I think you can imagine, a very long time after we close this switch, all of this charge has run out through this resistor and then this parallel combination. So this charge now becomes 0, and then it becomes constant at 0. So Q is 0, I3 is 0, I4 is 0, I5 is 0. So after a very long time, all of these currents are 0. Then one more part of this question is, at what time is Q equal to 3/4 of this value? So at what time t is the charge in the capacitor 3/4 of the value that it had immediately after we closed switch S2? So we know that the charge on the capacitor is going to follow a curve that looks like this. So this is Q equals Q initial e to the minus t over time constant. Time constant is going to be some equivalent resistance times this capacitance. In this case, the equivalent resistance through which the capacitor drains is R3 in series with the parallel combination of R4 and R5. So that is 1 ohm in series with 6 ohms parallel 3 ohms is 2 ohms. So that is 3 ohms. So then this time constant is 3 ohms times 1 microfarad is 3 microseconds. Then we're solving the equation. Q over Q0 is 3/4 equals e to the minus t over tau, where we know tau is 3 microseconds. Let's take the reciprocal of both sides first. So 4/3, that's Q0 over Q. That's 4/3 is e to the plus t over tau. Now take the logarithm of both sides. So we say the natural log of 4/3 is t over tau. That gives us t is the time constant times the natural logarithm of 4/3. That's 3 microseconds times the natural logarithm of 4/3. And that works out to be 0.863 microseconds. As if this problem weren't already long enough. At this time, what is I3? So we can use the loop rule, Q over C minus I3 times R equivalent equals 0. In this case, R equivalent is 3 ohms. It's R3 in series with this parallel combination of R4 and R5. That gives us I3 equals Q over R equivalent C, which is 1.5 microcoulombs. That's 3/4 of the initial charge. The initial charge was 2 microcoulombs, so 3/4 of that is 1.5 microcoulombs, and then divided by 3 microseconds is R equivalent times C. So this is 1/2 of an amp. So 0.500 amps. Whoa. I wrote that problem. Wow. That was a long problem.